derivative. So let us introduce del tau is del over del tau, and del sigma is del over del sigma. So tau of x nu would be del over del tau of x nu, and this would be of course my x nu, I have to remember that it is a function of sigma, tau and sigma. So this would be x nu dot. I'm not always writing the arguments x nu, we know them, they are functions of tau and sigma or sigma alpha. So del tau x nu is my x nu dot. Similarly, del sigma is del over del sigma of x nu, and this is x prime mu. Okay, there is only one special coordinate here, so I could call it del over del sigma. If one were to consider higher dimensional branes like a membrane or further, this we would not do. Okay, let's first consolidate string theory of 2D branes. Okay, so we have only one space coordinate, otherwise you will have more space coordinates. So this is, I can have just one convention x prime, which is the partial derivative of x nu with respect to sigma. Very good. And therefore now I could write g tau tau is eta mu nu del x mu over del tau del x nu over del tau. It is tau tau. Okay, so g tau tau, g tau sigma, g sigma tau, g sigma sigma. Okay, so we are considering the induced matrix on the worksheet and play around with this. So it is this, and this is equal to eta mu nu x mu dot x mu dot, and this I could write as x mu dot x mu dot, and this I could write as, maybe I could write it as x square, x dot square. Okay, so my x dot square would mean x, this product of or let me write one more step, x dot x dot, which means x dot square. So here the indices are suppressed, any one upstairs, one upstairs, one downstairs. Okay, very simple. So, and which is equal to this. Similarly, I could write t tau g tau sigma equal to eta mu nu, and why have I written here? Okay, mu nu. Okay, fine. Del x nu over del tau, and del x nu over del sigma. This is eta mu nu into x mu dot into x prime nu, and this is x dot mu, x prime mu. If I like, I can also write it as x dot x prime. Would that be sensible? Okay, it makes sense, right?
Can you turn on the light?
Yes, please.
Oh, thank. Good.
Good. Okay. She's happy. So
Yeah.
she likes that. I didn't realize so much. It's fine. So my g tau sigma turns out to be x dot x prime. Now we could write g sigma tau. So this is eta mu dx mu over d sigma dx mu over d tau This is eta mu mu x prime mu x dot mu. This is x prime mu x dot mu. This is x prime dot x mu. Right? We could do that. Okay, very good. And the last one is G sigma sigma. So this is eta mu mu dx mu d sigma dx mu d sigma. This is eta mu mu x prime mu x prime mu. This is x prime mu x prime mu. This is x prime dot x prime. I could even write it as x prime square if I like. So x prime square would mean x prime dot x prime. Here the indices are suppressed. Now I immediately see, if I look back, I can put, there is a mistake here, this should be mu. This is mu upstairs because I have eta mu mu here. Okay. So it is this, which is this, and which is G sigma sigma. And this tells me that I have written down all the elements of matrix for this G alpha beta matrix. Okay, I have all 4 of them here, and if you have to write the determinant of this, then for any future calculations, if you have to write determinant G alpha beta, then this would be G tau tau, G sigma sigma, and this would be tau tau is x dot square. No, what am I doing? Determinant of G alpha beta, not only this, I'm sorry, this would be, let me write it fully. This would be now x dot square, x dot x prime, x dot, and x prime square, right? And therefore this should be just x dot square, x prime square minus x dot x prime x dot. Is this okay? So we can write down the determinant of this matrix if and when we need. That's very good. Now we could I remove all this? I could remove this. Okay, good. And action of our string theory, we can take help of the fundamental concepts of the differential calculus. Okay, and according to that, we can write the area element dA, the surface area element dA. In the first place, we consider a space defined by G alpha beta, for a space defined by the matrix G alpha beta. I can write down the area element dA to be equal to minus. This is a very general result of differential calculus. You can write it for anything, whether irrespective of this need not be the induced metric. In any space which is defined by the metric G alpha beta, the differential area element can be written like this, and this is equal to square root of minus G and d tau d sigma, where G is determinant of